Good morning, welcome back. We have the second session of the second workshop on bias and fairness in AI. It's my great pleasure to announce our second keynote speaker, Professor Toon Calders. Toon is currently with the computer science department of the University of Antwerp in Belgium. He is a very active researcher and active member of research community in data mining and machine learning. He is editor of the Data Mining Journal. He was program chair of several conferences in the past, notably ECMLPKDD in 2014 and Discovery Science in 2016. Toon is well known for lots of his work in pattern mining, several problems in classification, and notably Toon is one of the pioneers of the area of fairness in machine learning. He studied how to measure and avoid algorithmic bias at the very start. And then notably, past year, he was awarded Test of Time award with ECMLPKDD and Data Mining Journal. And then in this area, he is currently leading a group of several researchers studying theoretical aspects of fairness in machine learning. And he is also actively organizing different events in this space, including workshops, special issues, and being a co-editor of a book on discrimination and privacy in information society. Toon, it's a great pleasure and honor to have you here. The floor is yours. Please go ahead.
All right, thanks for the kind introduction, Mikola. I really like it when you call me a pioneer. What I want to talk about today is a bit of a bird's eye view over the fairness and some observations that I have recently made and some observations that have been made in literature that I find quite interesting. And so basically what I want to address is, among others, the fairness accuracy trade-off and how that trade-off that is generally believed to be there in many situations actually does not exist. Normally, when you start a presentation about fairness, you would typically have a first slide showing something about data. If data may be biased, then your models will pick up the bias, and then it will be integrated into a decision procedure, which may lead to legal problems. And then we would say, okay, we want to study discrimination-free classification, because of discrimination laws not allowing us to use any of the classifiers that we learn if they do not satisfy certain conditions. For instance, taking the gender of someone into account when computing an insurance risk in order to set the fee for your insurance is illegal, even if you do it indirectly. Then typically we would come up with a couple of examples, like for instance, the racial bias in healthcare risk algorithm in the United States, where it turned out that because of the way the researchers in this United States study that tried to predict if a patient would be needing more care than other patients, there they used as labeling something that was racially tainted. And because of that, the predictions they were making and the errors that they were making actually included bias. There is also the case of Amazon with the AI recruiting tool and the very well-known Compass case. Now, all of these things, we have been researching them for 10, 15 years, have been picked up also at the European or at the legal level. And one interesting source of information is the high-level expert group that recently came up with a report where they identify 7 topics related to trustworthy artificial intelligence. For instance, about human agency and oversight, about robustness of the techniques that have been developed. Privacy is also a very big issue, transparency, and for us the most important, the part about diversity, non-discrimination and fairness. Then there is some societal aspects and accountability. If you have an algorithm that is unfair or biased, who is then responsible for the adverse effects that may result from that? And this high-level expert group also came up with a list of questions that could serve as a checklist for companies that have to implement the unbiased decision procedures and that want to use machine learning in their decision procedures. Now, how can they guarantee? And if you then look at the questions, you see that there is a lot about strategies that you need to develop to avoid creating and reinforcing unfair bias in the AI systems. And the first slide that I showed. So the diversity and representativeness of the data. If we learn from data that does not include people of color, let's say, and then you can assume that classification for those people will be less accurate, for instance, if it's face recognition software. And so these things you need to take into account, and also something about flagging. And one very interesting question in this list is the one about the definition of fairness, where the question that is asked is your definition of fairness commonly used and implemented in any phase of the process of setting up the AI system? Did you consider other definitions? Did you ensure quantitative analysis? And so do you have numbers that show that your algorithm is fair? And did you establish mechanisms to ensure fairness? And so fairness-aware classification, I would say, would fall in that category, and also probably some things like following up the system while it is running. And so this is the context in which I want to start my talk, or that I want to talk about, and I want to make some observations, basically looking through the glasses of, let's say that I'm a company that wants to implement this. What kind of problems do I encounter? And the very first problem that is encountered is, I think, that in the current state of the art, there is no way to make a well-founded choice for one or another fairness measure. There are plenty of fairness measures, but as a company, it's very difficult to actually choose one for your specific case. Here are some definitions and some notations that I'm going to use. It's just the standard notations that have emerged over the different years. So I'll use X for the variables that we will use to make our predictions. It's in bold because it's the vector of different attributes. A will be used for the sensitive attribute. For instance, age, gender, or ethnicity. And so this is A is equal to 0 will denote the group that we want to protect. A equal to 1, a privileged group. Then Y is the true label, and Y hat is the predicted label. If you then look at different definitions that have been given, then here are some popular ones. The first one, disparate impact. There we want to study how does our classifier affect the people or the objects that we are classifying. So we're going to look at the probability of getting the positive label if you're in the privileged group versus if you're in the protected group. And then typically people want these differences not to become too high. You can enforce that they should be exactly equal, or you can look at the difference between the two, put some bounds on that, divide one by the other, and then it needs to be close to 1. Another measure that you could take is equality of opportunity. And so there you're more looking at, okay, let's look at where my classifier is making mistakes, and I want these mistakes to be balanced. So basically, if Y is equal to 1, if my true label is equal to 1, I want that my prediction, the probability that my prediction is correct, is equal between my protected and my unprotected, my protected and my unprotected group. So that is typically, you do not want to have, if someone deserves to get a loan, the probability of him or her getting the loan should be equal independently, whether he or she is male or female. So you need to see it in that way. And then the third one is calibration, where basically we're going to say, well, if we assign a label, and this will mean that we'll put people into different groups, the interpretation of this group should be independent of the sensitive attribute. So let's say that we have people in court, and whether or not they are a high risk. So we will divide them, our predictions will be, we will put them in a high, medium, or low risk category. Now, if you look at the interpretation of the high risk category, and so Y hat, in this group, the probability of really being a risk, that your true label is 1, needs to be independent whether you're black or white in this specific example. So all 3 of them make sense, but which one should I pick? So I'm this company and I need to make my processes fair. And then the answer that we mostly give is, well, this is situation dependent. Depending on the situation, disparate impact might be more suitable, or calibration, or the equal opportunity. So let's look at a concrete situation and let's decide for this concrete situation what is the most useful measure. And so here, and the compass case is a very useful example. Most of you probably already know it. For those who don't know it, I will very shortly introduce it. And so in the compass stands for Correctional Offender Management Profiling for Alternative Sanctions. And it's a tool to predict the risk of recidivism. And so the label that is given, or that was given in the training data, is whether or not there was an arrest within 2 years after the collection of the data. So these were people that had to appear in court, and then their characteristics were recorded, and 2 years later whether or not there was a rearrest. So this was the data set that was used. Data is pending charges, is there a prior arrest history, pre-trial failure, and did they flee away before, residential stability, substance abuse. And so these were typical characteristics that were used. Then ProPublica, a consortium of investigative journalists, looked more deeply in this compass tool, and they showed that the errors that are made by the model are highly biased. And so, for instance, if you look at people that are labeled higher risk, but that did not reoffend, so you look at people that are not reoffending, did not reoffend after 2 years, how many of those were labeled high risk? And that's an error. It's a false positive. Then you see for white people, this probability is much lower than for African Americans. It's almost twice as high for African Americans. So this is a clear bias that exists in the model. If you look at the other type of error that can be made, and so it's someone who is who did reoffend, but was labeled lower risk. So he got a more favorable class than he actually, or he or she actually deserved. Then you see that the error there is in the opposite direction. And so that is clearly some bias, and this is clearly something that we want to avoid in our classifiers. So here you would say we should look at the errors and the balance of in errors. So equal odds or equal opportunity, and one of the measures on the previous slide, is the way to go if you're this company developing this algorithm. But then the company, Northpointe, defended themselves. And basically they defended themselves by saying, okay, maybe these statistics are there, but our scores are calibrated. And that is what you see on the graph on the right-hand side. It's taken from the paper that is cited there at the bottom. And there you see of those people that get low, medium, or high risk. And so those are on the horizontal axis. There it is given what is the actual risk in each of these groups. So if you get the low risk category, then you can see that about 30% of those, 35% are recidivists. And so these are errors that are being made. In the medium category, it's higher, and in the high category, it's even higher. So that is very good, of course, because we want our risk categorization to correspond to reality. And here you see within each of the groups, this percentage is not much different between black and white people. So here the lighter column is always the percentage for the black people, and the darker is for the white people, the recidivism rate. And we see it's more or less equal. There is no huge difference there. But where we do see a difference in this particular data set is the participation of each of the ethnicities in the different risk category groups. So that is what this black line is, that is here. So the percentage of people that are categorized as low risk, and 50% of those are black, and in the high risk, it's almost 80% of people that are categorized there are black. And so they're overrepresented in the groups here. So now if you look at the ProPublica study and why and did we get these statistics there, and then basically it comes, well, let's make it into a binary problem. You're high risk or you're not a high risk. If you then see where are the errors being made and which errors are being made, and then we see that for someone who is predicted to be in the high risk category, about 80% is truly high risk. So for 20% of those people, we're predicting that they're high risk, while they're not high risk. And so these are false positives, 20%. For people that are in the low or the medium group, so for them, we will predict that they are not a high risk. And so for those people, we're making the opposite mistakes for those who are contributing to these bars at least. And so for 50% of those people in the medium group, we're predicting they're not a high risk, but they recommit a crime, and in the low as well. So if we see how the errors are being made, and then all the false positives are being made in the high risk group, and all the false negatives are being made in the low risk group. And the false negatives, so these are the type of errors that we want. If you're criminals, that they let us go, and the red ones, and those are the ones that we do not want, because these are actually people that do not recommit crimes, but that are labeled high risk anyway. And then also, so this is summarizing what I just said, and black is relatively more frequent in high than in low and medium, and so they're overrepresented in these groups that are being treated less favorably than the other groups. So is this fair or is this unfair? You could dispute about this, but it is the case. Any classifier will make mistakes, and if different communities are differently represented in the profiles, it will mean that they are more likely or less likely to be subject to a specific type of error. So, and to summarize, if you look at ProPublica, what they want is actually equal opportunity. So basically they're saying, if you deserve to stay in prison, it shouldn't matter whether you're black or white for your probability to stay in prison. If you deserve to be released, it shouldn't matter whether you're black or white. And so if you look at it in probabilities, the probability of having y hat equal to 1, if your true label is 1, should not depend on it, whether a is equal to 0 or a is equal to 1. And the same for this other type of error. So the true positive rate and the false positive rate should be the same for both groups. While Northpointe is saying what it means to be high or low risk should not depend on your ethnicity. So if I label you as a high risk, then the probability that you are truly a high risk should be independent of a equal to 0 or equal to 1. Both of them make sense, and for both of them, and what I do I teach a course about fair machine learning, and what I do is I present this case to the students, and then I ask to them, okay, let's have a vote. Who thinks this equality of opportunity should be present in an algorithm, otherwise it's unfair? And typically all of them agree that this needs to be the case. Who agrees that calibration needs to be there? And mostly 3/4 would say, okay, yes, it's fair enough. Both of them should be there. And so basically what we want is, if we look at low risk and the calibration, so this is what is happening in the Compass case. 1/3 here in the low risk is recommitting crime. It doesn't matter what is your ethnicity. 2/3 in the high risk category. But if you look at it in that way, in the other direction, if we look at how many errors are being made, what is the probability of being high risk? If you're truly a high risk, it's much higher here than for the white people. So can we satisfy both of them at the same time? So according to the vote, then most people agree, okay, it should both be satisfied. But then there is very bad news, that it can be proven that both together can only be realized under very exceptional conditions. And this appeared in the paper of Kleinberg and others. And basically this very exceptional condition is either there is perfect predictability. And so this is a screenshot from the movie Minority Report, where they can perfectly predict crime and then decide to look up criminals even before they were able to commit the crime. So we are far away from that, and whether that's ethical or not, that's another question. So that's one thing, because if there is perfect predictability, the errors will be balanced because there are no errors. The true positive rate will be 1, the false positive rate will be 0. Or if there are equal base rates? Well, if the two communities have an equal recidivism rate, then it is possible to build a classifier that satisfies both conditions at the same time. So here in a situation that a company needs to decide between different fairness measures, all of them have good reasons. And like here, this compass case, and both fairness measures should be satisfied, you could argue, but it is impossible to do so. Apart from that, I also want to point out some initiatives that have been taken to resolve this case. For instance, this is a paper from people working at AXA that are confronted with these type of problems, and they try to build this type of taxonomy in order to identify the most appropriate fairness measure metric for a particular application. And it looks like this big decision tree, and then depending on the situation, is it policy related, the fairness that I want to have? Is it something like my data is maybe correct, but I want in future that it becomes more equal, and so there is a affirmative action, or is not policy related? Do I want equal base rates or not, etc., etc.? And then based on those questions, this taxonomy end up with the different fairness measures. But I would say that it is still very unsatisfactory, and it's a real problem if we want to that these things are adopted in legislation. Well, we will have to answer this type of questions. In what situation do you need to take which fairness measure? So that was my first point. I think currently there is no way to make a well-founded choice for fairness measures, or at least the theory is lacking for that. And a second point that I would like to make is, if you look at the algorithms that we have developed, that many of those, well, fairness intervention is, I put it a little bit strong here, but are often synonym for window dressing. So the classifier that we learn superficially looks fair, but in reality is not necessarily more fair than the classifier that we started out with. And so let's look at, for instance, equal odds. I do not want to pick on some particular authors or algorithms. I will also present some of these negative results for my own algorithms. But this is a very nice algorithm and very illustrative, I think, for the point that I would like to make. So Hart and others, they were the ones who proposed, instead of demographic parity, to use equalized odds. And so equalized odds is basically the requirement of the ProPublica research investigated journalists. And basically the observation that they are making is, what I want if I have equal odds, I want that the true positive rate and the false positive rate are equal for both A equal to 0 and A equal to 1. And so for both my communities, the true positive rate and false positive rate need to be equal. So basically, I want to make mistakes at the same ratio between the two groups. And so this means that we can basically draw two AUC curves. Let me immediately go to the next one. Because an AUC curve and ROC curve, sorry, an ROC curve gives you the relationship between the true positive rate and the false positive rate of your algorithm. And each of the points on your curve represents a certain trade-off that you can optimally achieve. So we can draw one curve for the, let's say, for males, my classifier applied for males, and then the green one is then, for instance, my classifier applied to females. At the point where they intersect, if I put my threshold for males and females in a different way, so that I end up in this point for both of them, and that is my classifier, then I will have a classifier that satisfies equal opportunity, and I can do this in a way that I get actually a optimal accuracy or an optimal cost, whatever I want to optimize. And but then what should we do in cases where there is no natural intersection point, or the natural intersection point that we have as a too low accuracy for my application is not suitable? And so suppose that we have here the true positive rate, the false positive rate. red is for males, blue is for females, for instance. So it's much more easy to predict for the females than for the males. Maybe we have more information because of some subtle biases in my data set. Then one thing we can do in order to make them intersect is we can take a classifier on this blue curve, a classifier for the females, and we can artificially make it worse in order to meet this point here. And that is also what the algorithm is doing, and it's even provably optimal. Now, if you want to make a classifier which satisfies equal odds and is most accurate, then this is a valid strategy to go to actually change the classifier here. So this means that when we will be classifying, and we will first see if it's a male, then we will use our optimal classifier here. If it's a female, then we will use the optimal classifier for the female. We will make the prediction. If the prediction is positive, we will toss a coin. If it's heads, we will predict positive, and otherwise we will predict negative. And in that way, we can actually have this classifier in the intersection. And I would argue this is not really very ethical. And basically what we are doing is, you have this dilemma, our provable optimal classifier will make mistakes on purpose. And we're in this situation, and there is this train, and we are going to hit one person or 5 persons, which decision should we take. And we have males and females, and we see that there are differences in error rates. If we're going to change our classifier, it may become better or worse for one of both. And basically what our algorithm is doing is this. Our solution, we just run over one set of people, and then the other we just shoot in order to compensate and in order to make it fair. And the reason for this is, of course, algorithms are cynical. They want to keep accuracy high while becoming more fair. And for an algorithm, it's equally interesting to demote a person with who is in the privileged class, or to promote a person who is in the other class. And so if we put it as a constraint on our algorithm, we can imagine, and we can be certain that they will make this trade-off in an optimal way. For instance, if there are many more people in my privileged group than in my so let's say that there are many more privileged people than unprivileged people, then the second one will be more interesting, because you change one person and the fraction of your data set, that the probability of having a positive label changes much more than when you would change it in a bigger group. And so depending on the situation, however, one could be more appropriate or interesting than the others. But algorithms don't care. So let's look at an experiment. Here I took my own algorithm already from some time ago, where we do reweighing, which means that we will we take our data set, we observe that there is a bias in the data set, we resample the data set in order to remove the bias, and then we learn the algorithm. And this provably removes disparate impact, for instance. So I run it on the adult data set, and here you see the results. And so this is the confusion matrix for the bias classifier. So I have A equal to 0, I have A equal to 1. So this is my protected community, and this is my privileged community. And we see that there is clearly a big problem here in this row. Now, if you look at the predictions, so this is the true class, y is equal to 1. Those who are truly positive, most of them are actually predicted to be negative in my protected class. And while here in my unprotected class, in my privileged class, it's the other way around. It's not great either, but it's better. So when we would correct this situation, we would expect that it would move a point from here to there for y equals to 1, so it will make some of these predictions correct. If you look at what the intervention is actually doing, so in order to get the intervention, you should add up these numbers to the table here and just summarized. So if we look at the ones with y equal to 0, so those who are having a negative label, then we see that a lot of them will be predicted to be positive. So we'll actually on purpose start making mistakes in my a equal to 0, and we will be predicting some of those to actually be positive. And the green ones are always the arrows, and that represent the cases that we would like to see. And this is much less outspoken. There are much less that are truly positive, that are predicted positive. There are actually more errors being introduced. And here, and the other way around, and then we see that for a lot of those who truly have the positive label in the privilege group, now we're going to predict the negative label. Is this result dramatic? No, I would say some of this is to be expected, and we are not perfect, so we cannot really single out, okay, there were mistakes here. We're only going to correct mistakes. But this is a pattern that you see in a lot of those algorithms. When they start correcting, they will actually, they don't care that much in which way they correct, and sometimes they will just demote. And so this is the shooting with a equal to 1 in order to make it more fair. So that is a second point and that I would like to make. First point is very hard to decide on a measure for fairness. Second one, even if we can decide about a measure of fairness, the algorithms are resolving the situation, but not always in the way that we have foreseen. Then the third point is, and there is no fairness accuracy trade-off. And let me first state what the fairness accuracy trade-off is. It's actually, if we look at all the feasible models, and then we restrict those to the models that are feasible and fair according to our fairness definition. Then if we look at the optimal model, so the most accurate model in the set of feasible models, and we restrict ourselves, okay, we do not want to have any feasible model, but only one that is fair. So we have the most optimal fair model. Then we will, it's logical that you will sacrifice some of the accuracy in order to achieve fairness in your predictions. And it can even be proven, and this has been studied theoretically. So if you have a classifier, for instance, we are giving loans or no loans to males and females, then basically what we can change is we can change 4 parameters. The males that got a positive label, we can change to males with a negative label, males with a negative to males with positive, etc. Same for the females. And then you can prove that the classifier or the change that you're making is optimal if you do not change. So suppose that females are the ones that are disadvantaged and needs to get more loans. It makes sense that we will never change a negative label for a male to a positive label for a male, or a positive label for a female to a negative label for a female. And if you do it in that way, there will be a linear relationship between accuracy, the optimal accuracy that you can achieve, and the remaining bias that you will have in your data set. And so this is the trade-off between accuracy and dependency. And so basically we're only going to make these type of changes where we will move people from one group to the other. So then recently there was this quite interesting paper of Wick and others, where basically they said, and this is a very good observation, most of us realize it at some level, but still we're ignoring it when we're writing papers and evaluating all our algorithms. They're saying, okay, the most accurate fair model is less accurate than the most accurate model overall, but, and this is a very strange way of looking at it, because we started out by assuming that our data had bias. So the labels that are in our data are not correct. And so we're going to move away from the labels that are in our data to new labels. But when we're evaluating the performance of our algorithm, we will still look at our data set and evaluate with respect to our biased labels. And so basically they're saying, so you should not optimize accuracy on the tainted training data, but optimize expected accuracy for fair test data. And so they run some experiments. They take the data that is related to the compass case, where they look at fairness versus accuracy. And in one situation, they look at a biased ground truth, in another case to an unbiased ground truth. So basically what they did, they took the data and then they added some manually some additional discrimination, such that they have a data set in which there is direct discrimination present. They evaluate the fairness of their algorithm versus the accuracy of their approach, in this case a weighted F1 score. And then you see if my algorithm becomes more fair, it moves away from the labels in my data set. And so it also becomes less accurate. However, if they test it on the unbiased ground truth, where they didn't introduce manually direct discrimination, and then basically you see if that your accuracy can actually increase, and because when your fairness is increasing. And this is, I think it's a very strong point that you're making. There is not really a trade-off between fairness and accuracy, and because we're assuming that the labels are incorrect, and so it's not fair to be measuring our accuracy with respect to the biased labels. But then what should we do, and how can we look at this, and how can we decide in between these different situations? And there I see another very interesting work that is basically about that we should separate machine learning from policy, bias correction, or affirmative action, and these are two different things. Bias correction means we assume something is wrong in our data set. So we're going to learn an algorithm, but not trust the labels in our data set for 100%, and traditionally impose some constraints. Affirmative action means, okay, and we assume that our classifier is giving positive correct results, but we want to change the predictions because we want to reach a certain outcome in future. So that is, and those are very different things. Like I said, there are many competing definitions of fairness, not a single best one. Which one is suitable depends on the situation. Friedler and others try to systematize the description of such situations by considering three spaces. And these three spaces represent like what are instances really, how do we observe them, and what do we want to decide about them. So the construct space is where the, well, it's just the true world with true characteristics. In the observed space, and these are the things that are in our data set, that is what we observe in our data set. And then in decision space, in the end, we want to have the outcomes, we have the outcomes of our classifier, and there are mappings between these different spaces. For instance, the mapping between the construct space and the observed space expresses in data gathering what information might be lost, what biases may have been introduced. The mapping that we learn is between the observed space and the decision space. And what I find really interesting in their approach, and I think is very useful to build upon, is an axiomatization, where they look at what do we know about the construct space, what do we know about this mapping, and what should we enforce here. And these are different things that we should look at in different ways and also treat differently. What do we know about the construct space? And so this could be, there might be situations in which we want to enforce demographic parity. And so we want that black and white have same access to, let's say, education. Why is that? And because we have a deep belief in the construct space that black and whites are equally capable, equally intelligent. So they should receive the same schooling. It doesn't make sense to make a difference between them, even though maybe in the observed space, if we look at test results or whatever, we may observe a difference that is inconsistent with our construct space. Well, then that is the result of the mapping that we have from the construct space to the observed space. Maybe there is some sample bias, or maybe there are some underlying reasons, and the characteristics that we observe are only proxies. So that's one part. Another part is, okay, what do we want to have in the end? Maybe we want to have affirmative action. So we want to increase participation of one group versus the other group. Well, this is something that we should solve in the mapping here and not in our understanding of the mapping that we have here. So I'll skip over this, and because I see I'm already talking for quite some time, I want to leave some time for questions as well. So the axiomatization, axioms express the way that spaces interact. And the word axiom is well chosen here, I think, because we cannot prove that an axiom holds or not. This is something that we assume about our data. And for instance, that we are all equal, and we assume that both communities are equally capable, for instance. So that is in the construct space a condition that we can impose, or we can impose restrictions on how do the construct space and observed space interact. And then a WYSIWYG, what you see is what you get, is an acronym that stands for, well, we observe perfectly what is there in the construct space, and that will not always be the case, depending on which of the two you're assuming, and one intervention or another intervention might be more appropriate. So if you look at the conclusions, then people that are studying balancing in errors, they implicitly assume this WYSIWYG, and that the labels we're observing are the true labels. So it makes sense to require equal odds, and that the errors need to be balanced between the two communities. If you assume that there is structural bias, then you may adopt the we are all equal. And so we see in our data set they're not equal, but we assume that both communities are equal, and then this is the we are all equal that you're assuming. But here there is some misalignment actually between the way we are measuring versus what we actually want to do. And this is then again related to this fairness accuracy trade-off. Different types of biases require different interventions. And legal requirements are policy. Direct discrimination is a distortion between the true labels and the recorded labels. So that requires a different treatment than a legal requirement. But now I'm starting to repeat myself a little bit. And basically the point that I want to make is that in my opinion, the machine learning part should concentrate on estimating probabilities accurately, which means that in that part, the machine learning part, we should take care of direct discrimination, for instance, or indirect discrimination, where there is a distortion between true labels and recorded labels. But affirmative action is something that basically is policy, and we should treat in a separate step when we turn probabilities that we learned as well as possible into decisions. And I think that this distinction is not really made currently in the algorithms. So then the final point, to correct bias, we need to know how it was introduced. And this is basically a glimpse into the research agenda in future for my research group. So if we look at the data set, and this is how an algorithm looks at the data set, it's just all anonymous. It does not have any interpretation of what the attributes and the labels mean. And then we can wonder, is this data set fair? In all cases, the predicted label is the same as a true label, only here we're predicting a 1, but it's actually a 0. Well, it depends how we fill it in. If we say that this is a gender and whether someone has a diploma or not, and here we observe that out of the 3 people in the data set, 2 that went to university, 2 of them were hired, and then the fact that we are here also making a prediction and making the proportions equal between females and males is probably a correct decision. If we fill it in differently, so it's the same data set, but just replaced by other constants, and now it's males versus females, and we want to predict whether someone is a high risk for car insurance, then basing yourself on the hobby of a person in order to decide whether someone is high or low risk is not a good way to go. And because probably it is males are more risky than females when driving a car. And we're using the hobby as a proxy to decide whether or not to give the high risk label here. So the implicit assumption that we make on the data differ, and therefore also our perception of what is fair, and this should be incorporated. And so here, so how can we exploit information on a bias process? What is the correct way, in my opinion, to look at it, solving some of the problems that we have, is by assuming in the construct space that there is a true fair but unobserved label G. So G stands for ground truth. We only observe a potential unfair label Y, but we do have some information about how Y came from G. I think in many applications, if you look into deeper and try to understand the application, that is often the case, that we can understand how they are related to one another. Well, then the objective will be, and we will no longer have to choose between will we use equality of opportunity or demographic parity. No, our goal will be as fair as possible. When are you fair? If you make correct predictions. And so our predicted label needs to be as close to the ground truth label that we do not observe, but we have this relation here. And then we can study that mathematically. I will skip over that. But if you realize to this and to do it in this way, it gives you a lot of tools. It will allow us to check if data is consistent with the presumed model and with the presumed way that discrimination is introduced. And we can reverse engineer the label G. So there will no longer be an accuracy bias trade-off. Fair will be predicting the true label, and no need to select fairness measure anymore. I think it's much more natural to state bias process and assumptions that we have on the data. So to summarize, I think, or the point that I would try to make is that currently there is no way to make a well-founded choice for one or another fairness measure, or at least not an easy one. It is highly non-trivial. Fairness interventions do not always do what we think they do. And sometimes they just are some window dressing, making the statistics match, but they're not really making the situation more fair. The fairness accuracy trade-off is only a artifact of the fact that we're measuring our accuracy on labels that we assumed are biased, because otherwise we would not have a fairness intervention. We should separate machine learning from policy on the one hand, and bias correction, bias that there might be in the data due to direct discrimination, labels that are incorrect, correcting for that, and definitely belongs into machine learning. The affirmative action, that is policy and should be treated in a separate step. I'm not saying machine learners cannot study this step, but it's important to separate the two of them. And the last point, to correct bias, we need to know how it was introduced. Voila, that concludes my talk, and with the main takeaway that, in my opinion, ethical machine learning is maximizing accuracy in a fair world.